Okay, so today we're going to be talking about logarithms and natural logarithms. We're going to start that discussion by continuing our classroom discussion about how to rewrite logs as exponents. Whoops, go back here. Okay, so remember from class we have that looping technique. So we start at our base, we loop around to the exponent, and then around to the value. So we can rewrite this as 4 to the x power is equal to 64. But we know that 64 can be rewritten as 4 cubed, so we can then say that x is equal to 4. So same thing over here, we go from our base around the circle, so we can say that 343 to the x power is equal to 7. And then we can rewrite 343 as 7 cubed. So 7 cubed all raised to the x power is equal to 7 to the first power, which means that we can say 3x is equal to 1, so x is equal to 1/3. Or in other words, we could say that the cube root of 343 is equal to 7, which is why the exponent has to be 1/3. But if we go to our bottom two examples, now we have this situation where there's no number written here. So there's nothing written here. And when that happens, when there's no number written there, we assume the base is 10. So this is called a common log. Go off here. Which is base 10. So we would write that as log base 10 of some value. But when we have a 10, we just don't write it. So it's just our assumed base when it's not there. So we can rewrite this as 10 to the x is equal to 100. And we know 10 squared is equal to 100. So rewriting it that way so they have the same base, we can then say x is equal to 2 over here. And then same thing over here, we have base 10. So looping around, we have 10 to the x power is equal to 0.0001. And we know from scientific notation that if we want to move the decimal point, we could go 1, 2, 3, 4. So we're moving it 4 places. And since we are making a very small number, we can say that that is really 10 to the negative 4th power. So x has to equal negative 4. Okay, so we can also use logarithms to solve different types of equations. So say we have this equation 10 to the x is equal to 7. If you are solving for an exponent, that tells you want to rewrite it as a logarithm. So if we rewrite this, we know that we have our logarithm form is log of some base of the value, or the answer, is equal to the exponent. So if we rewrite ours, we have log base 10, and our answer is 7, and that needs to equal the exponent of x. So that's a common log, so we don't have to write the 10, so we can just write this as log of 7 is equal to x. Now this is a calculator type of question, so we're going to go to our graphing calculator. So we're going to go to the calculator, and we're going to type log on our calculator of 7. So the log key on your calculator is common log. It's always going to use base 10. And so our answer is 0.845. That. Working with some new tech here today. We're going to see how this works. We have 0.845 is approximately equal to x, which would tell us that if we look back at our original equation, 10 to the 0.845 power should be approximately equal to 7. Okay, so we can also use logarithms to solve for different types of equations. So the last equation we were solving for the exponent, so we needed to use a logarithm. But here we're solving for the answer. So we're going to rewrite this log, and we're going to include the base. So log base 10 of x is equal to 2.873. So we're going to rewrite this as an exponential to look at what we're actually solving for. So if we rewrite it by looping, we see that 10 to the 2.873 power is going to be equal to our x value. So as soon as you have that, as soon as you have x isolated, you're going to have calculator problem. So we're going to type in 10 raised to the 2.873 power, which is going to be 746.45 is approximately the value of x. Okay, so we can also use logarithms in different types of equations and different types of numbers. So one application of logarithms is in interest, and we see this when you actually solve backwards for interest problems. So just a little bit of review from compound interest. Compound interest is when you take the amount of money in your bank account and you apply the interest rate several times. So like you would apply it the first time, and then the second time you would include the whole value, including priorly earned interest. So this equation should look fairly familiar. A equals P times 1 plus R over N to the NT power. So what do all those letters stand for? A stands for the amount in your account. P stands for the principal or the starting value. R is the rate, it's the interest rate. And remember, if we have an interest rate, we have to write it as a decimal value instead of a percentage. N stands for the number of times compounded in 1 year. And then T stands for time in years. So we're just going to do a quick little review problems. You should have used this formula before. So we have a savings account that starts with a balance of $100, so that's our P value. It's compounded quarterly, which means it's compounded 4 times a year, so N is 4, at a rate of 4%. So here's our R, and to write that as a percent as a decimal, we're going to do 0.04 instead of 4%. And we want to know how much will be in your account at the end of the year. So our time here is 1 year. So we're just going to plug into our formula. So we're finding the amount A for a principal value of $100, and then 1 plus our rate, so 0.04. We're compounding 4 times. And then we're going to do 4 times 1 for N times T. So if we simplify this, we're going to do 100, and then 0.04 divided by 4 is 0.01. So we're going to 1.01, adding those things together, and then 4 times 1 is 4. So we're going to type this into our calculator, 100 parentheses 1.01 raised to the 4 power, and that's going to give us approximately $104.06 at the end of 1 year. Now that's one type of way to earn interest on your account. Another type of interest you can earn is called continuous compounding. So continuous compounding means that the amount of money in your account is being compounded all the time, hence the word continuously. So it's not even just every second, it's every millisecond, it's every single instance of time it's being compounded. So when we have an equation like that, our formula to use is called PERT. So we have A equals P times E to the RT. So E, you might have seen before, E is a special constant like pi. And the value of E is approximately 2.718. So in this equation, P, R, T, and A all still stand for the same thing. E just replaces that 1 plus R over N interest rate formula in the middle. So we're going to just look at the same account, but now instead of compounding it quarterly, we want to know how much money the account would have after a year if it's compounded continuously instead. So we're going to plug into our PERT formula. So A equals our principal of 100 times E raised to the 0.04 times 1 power. So our rate was 4%, our time is a year. So if we just type that into our calculator, at the end of 1 year, we would have approximately 109.65 cents. So you can see if we look back at our numbers, we have about $5 more, $5.50 more between the two different types of compounding. So now that we have that number e in our repertoire that we've talked about it, we have something that's called the natural logarithm. So a natural logarithm is just log base e. So if we use that special constant e as a base, we call it a natural logarithm. And when that happens, just like when we have a common logarithm, we don't write the 10. If we have a base e logarithm, we abbreviate that as ln for the natural log. So whenever you're dealing with natural logarithms, you just want to remember that you have a log base e. So if we're looking at these different types of equations, we would have ln of 0 equals x. Well, that's really log base e of 0 is equal to x. And if we loop our value around, we have e to the x power is equal to 0. So I want you to stop and think. Can you ever raise a number to a power and have it equal 0? Well, the answer is no, right? If you raise anything to a power, you have to have a number coming out as your answer. You're never going to hit 0. So we actually have no solution here. If we look at our second example, again, we're going to write it as log base e of 1 equals y. We're going to loop around to rewrite it as an exponential, and we're going to get that e to the y power is equal to 1. But we know from the zero exponent theorem that any number raised to the power of 0 is equal to 1, so y has to equal 0. And then looking at our last one, rewriting again, we have log base e of e is equal to z. Looping around, we write e to the z power is equal to e. But remember that e has an invisible exponent of 1, so z must equal 1. Okay, so just an application of a different logarithm property. So under certain conditions, the height h in feet above sea level can be approximated from the atmospheric pressure P in pounds per square inch, or PSI, using the equation h is equal to the natural logarithm of P minus the natural log of 14.7 divided by negative 0.000039. So we know that human blood, quote unquote, boils at 0.9 psi. So that's the pressure that our bodies would not be able to handle because we would then die. So we want to know about at what height above sea level would our blood boil in an unpressurized air cabin. So that's why when you fly in an airplane, they have to pressurize the cabin so that this effect doesn't happen. So we know that we have 0.9 psi. So psi is the letter P. So all we're going to do is plug in for P. So we're going to say h is equal to the natural log of 0.9 minus the natural log of 14.7, all divided by negative 0.1234039. So again, we're going to go to our calculators real fast. Oh no, I don't know what I did. Hang on a second. Get out of that zoom feature. Okay, we're going to go out to our calculator now. So we're going to go over to the calculator, and I'm just going to show you where the button for the natural logarithm. It's right under the button for your logarithm. So we're going to just carefully type into our expression. So we had the natural log of 0.9, closing our parentheses, minus the natural log of 14.7. So we're going to find the value of our numerator, which is negative 2.793, and then we're going to divide it by that negative number in the bottom. So we had negative 0.12340, so one too many in there, and then 39, still one too many in there apparently. So that's going to give us approximately 71,621 feet above sea level would be the pressure, would be the height where our blood would boil in an unpressurized cabin. So from our calculators, we know that h is approximately 71,621 feet above sea level. Oh, So that is the end of it. Okay, so you have two OYO questions to do. They both deal with that interest formula that we talked about. So the first one is $720 in a continuous compounding situation. And then in number 2, I want you to look at that account balance after 4.5 years if you use continuous compounding and if you go back and then were to just do it with quarterly compounding. Which one would give you more money and how much more money?